Hello everyone, welcome to the lecture again. Today we are going to discuss the harmonic oscillator, particularly the simple harmonic motion. So remember, for stable equilibrium we have discussed that the potential energy should be minimum. Okay. So this we already know that for a stable equilibrium the potential energy should be minimum. Okay, this implies that if V is the potential energy, then dV divided by dq, where q is the coordinate, should be equal to 0 and d2V over dq square should be larger than 0. So, if let us say this is the x axis or this is q and we have V, then the particles remains at minimum potential energy. So, let us say the particle is here and we have taken this as V naught. This can also be 0 depending upon where you set the reference, and now let us say you displace this particle by an amount x naught. Okay. So, in that case a force is going to act on the particle to bring it back to the equilibrium. So, let me state it here. If we displace the particle from a stable equilibrium, then a restoring force, and the value of the restoring force will be minus dV by dq, okay, F equal to minus dV by dq will act on the particle to bring it back to the equilibrium. Equilibrium position. Okay. Now, this V, as I said, this is a function of fx because V is varying as a function of x. Now, this function of fx I can expand using the Taylor expansion about let us say x equal to 0. Okay. So, in general this V, which is equal to fx, can be expanded about x equal to 0. This is the position wherein we have a stable equilibrium using the Taylor expansion. Okay. And in general any function fx using Taylor expansion can be written as f a plus x minus a over factorial 1 f prime a plus x minus a whole square divided by factorial 2 f double prime a plus dot 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 dot, wherein f prime a means df divided by dx. Okay. Here, as I said, we are expanding it around the stable equilibrium. So, therefore, your A has to be 0. Okay. Now, let me write down for f we have potential Vx, Fa will be V naught plus x over factorial 1 is 1 and A is 0. So, therefore, it is x dV by dx at x equal to 0 plus x square divided by factorial 2 d2v over dx square plus dot 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 dot. Now, as I already said that for the stable equilibrium your dV by dq has to be 0. So, herein you have dV divided by dx at x equal to 0, because that is where I have the stable equilibrium. So, therefore, this has to be 0 and d2v over dx square at x equal to 0 is positive. Okay. And let us say this d2v over dx square which is positive, let us say its value is equal to k. Okay. So, therefore, I have v equal to, so we are looking at this equation, we have v equal to v naught plus this term is 0 because dV by dx is 0 plus x square over factorial 2 into k. So, k x square divided by factorial 2. Similarly, we have higher order term. So, let us say the other constant is k1 x to the power 3 divided by factorial 3. Okay. Let me call this equation number 1. Okay. So, k1 is d3v over dx cube. Okay. Now, we have also seen that the force that is acting on the particle when you move it from the stable equilibrium is minus dV by dq. So, herein it is minus dV by dx. Okay. So, F is equal to minus dV divided by dx, and from here I can find out what is the force that is acting on the particle. So, therefore, F is equal to, so let us differentiate equation number 1, V naught is a constant value. So, therefore, that is equal to 0 minus x square differentiation is 2x. So, we get and 2 will get cancelled with factorial 2. So, we have k x minus k1 x square over 2 minus similarly k2 x to the power 3 divided by 6 minus dot 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 dot. Let us call this equation number 2. Okay. Now, assume that the displacement is small. So, herein when we move this particle, let us say we move it by a small amount. In that case, so let me write down, if the displacement is small, then the higher power of x can be negligible because x is small. So, therefore, x square and x to the power 3 they will be even smaller. Okay. So, we can drop this term under the assumption that the displacement is small. Okay. So, in that case we have F is equal to minus kx and your V will be V naught plus half k x square. Okay. Now, let us look at simple harmonic motion. Okay. Let us say I have a spring and the spring constant of the spring is k and a mass m is attached to the spring and this spring is stretched by x naught. Okay. So, in that case now we can analyze the motion. So, we have the equation of motion summation Fx equal to m x double dot. So, herein the force that is acting on the spring is minus k times x. So, we have m x double dot equal to minus k x, okay, from here. So, this is let us say equation number 3. Now, also note that this V naught I can put equal to 0 by choosing an appropriate reference. So, for example, herein if this curve V touches the x axis, in that case V naught will be 0. So, to analyze this equation of motion, let us define a quantity omega equal to square root k by m. Okay. So, let us define omega equal to square root k by m. So, in that case the equation of motion becomes x double dot equal to minus k by m is omega square into x. Okay. Now, its solution will be x equal to a cos omega t plus b sin omega t. Now, we can check whether this solution is correct or not. So, for that let us find out what is x dot. X dot is dx divided by dt. So, that will be minus a omega sin omega t plus b omega cos omega t. Similarly, x double dot will be minus a omega square cos omega t minus b omega square sin omega t, and from here I can take omega as a common factor. So, minus omega square, and then we have a cos omega t plus b sin omega t, which is equal to x, and this equation is similar as equation number 4. Therefore, the solution x equal to a cos omega t plus b sin omega t satisfies equation number 4. Now, the values of this constant a and b can be determined from the initial condition. So, let us say at t equal to 0, this is the situation that we have, and let us put our reference axis over here. So, at t equal to 0, we have x equal to x naught, and let us say at this instant the velocity of the mass is x naught dot. Okay. So, this is the initial condition. Let us put it in the solution. So, we have at t equal to 0, we have x equal to x naught and x dot equal to x naught dot. Therefore, if I put it in this solution, at t equal to 0, sin omega t will be 0 and cos omega t will be 1. So, therefore, x naught is equal to a, and let us put the value of x dot over here. So, at t equal to 0, again this term will be 0 and cos omega t will be 1. So, therefore, we have x naught dot equal to b into omega, and put this in the solution. So, we have x equal to x naught cos omega t plus x naught dot over omega sin omega t. Let us call this as equation number 5. Now, note that we have taken x equal to a cos omega t plus b sin omega t as the solution of equation number 4, and we have seen that indeed this solution satisfied the equation number 4. We can also choose another solution of equation number 4, okay, which is x double dot equal to minus omega square x, and let us choose this solution x equal to c sin omega t plus phi. Okay. Let us find out what is x dot in this case. So, x dot will be c omega cos omega t plus phi, and x double dot will be minus c omega square sin omega t plus phi, and this I can write down as x double dot equal to minus omega square x. So, this implies that x equal to c sin omega t plus phi satisfies the equation x double dot equal to minus omega square x. So, therefore, that is also a valid solution. Here the constant are c and phi, and their values can again be find out from the initial condition. And remember the initial condition, we have at t equal to 0, we have x equal to x naught and x dot equal to x naught dot. Okay. So, let us put this above in the equation. So, at t equal to 0, we have omega t equal to 0. So, therefore, I have x naught equal to c sin phi. Let us call this equation A, and we have x dot equal to x naught dot. So, herein let us put omega t equal to 0. So, we have c omega cos phi, or x naught dot divide by omega equal to c cos phi. Let us call this equation B. So, we have two equations and we have two variable that we want to find out, phi and c. Okay. So, for that let us square and add them. Okay. A and B. So, we have x naught square plus x naught dot square divided by omega square equal to c square sin square phi plus c square cos square phi. C square I can take outside and sin square phi plus cos square phi equal to 1. So, therefore, we have this equation. Therefore, c will be square root x naught square plus x naught dot square divided by omega square. Okay. Now, remember earlier we have find out the values of A and B. So, A was x naught and B was x naught dot over omega. So, therefore, I can write down the relation between C and A and B. Okay. So, you can see that C is nothing but square root A square plus B square. Now, to find out the value of phi, so let us divide A and B. So, we have tan phi equal to x naught over x naught dot omega. Okay. And again you can see that phi is also related with A and B, okay, because A was x naught and B was x naught dot over omega. So, therefore, phi is nothing but tan inverse A over B. Okay. And let us put the values of C and phi above, okay, in the solution. So, we have x equal to C, which is square root x naught square plus x naught dot square over omega square sin omega t plus tan inverse x naught omega over x naught dot. Let us call this equation number 6. So, we have find out two solution of the simple harmonic motion. One is given by equation number 5 and the another one is given by equation number 6. Okay. Since they represent the solution of the same simple harmonic motion, therefore, the solution has to be the same. So, let me write down that equation number 5 and 6, they represent the same time dependent motion. Okay. Let me just summarize the result. So, we have the equation of motion of simple harmonic motion, which was x double dot equal to minus omega square x, wherein this omega was square root k by m. One of the solution was x equal to a cos omega t plus b sin omega t, and the another solution we have taken x equal to c sin omega t plus phi. Okay. Now, let us plot the motion. So, on the horizontal axis, now we have time t. Initially at t equal to 0, we has x equal to x naught. Okay. Now, the maximum value of x can be when sine is maximum and its maximum value is 1. So, therefore, x can be c at max, and since it is a sine function, so therefore, the motion will be something like this. Okay. Now, one complete oscillation is called the time period t, and let us find out this time period t. Okay. So, we have x equal to c sin omega t plus phi. Let us increase t by 2 pi by omega and see what happens. Okay. So, we have x equal to c sin omega, t is t plus 2 pi by omega plus phi. So, this I can write down as c sin omega t plus phi plus 2 pi, and sin 2 pi plus theta is again sin theta. So, we have c sin omega t plus phi. So, this is the same value that we have earlier. So, that means if I increase t by t plus 2 pi by omega, we get the same value. Okay. So, this implies that 2 pi by omega is nothing but the time period. Okay. So, therefore, t equal to 2 pi by omega, and remember omega was square root k by m. So, therefore, this becomes 2 pi square root m over k. So, total energy will be the kinetic energy plus the potential energy. Okay. Now, we already know the potential energy of the harmonic oscillator V. V is equal to half k x square, because V naught is 0. So, we have half k x square, and the kinetic energy T will be half m v square. So, V is x dot square. Now, we have to find out what is x dot. Okay. So, remember the equation of motion. So, equation number 4, we have x double dot equal to minus omega square x. So, we have x double dot equal to minus omega square x. This was the equation of motion. Let us multiply this equation of motion by 2x dot. Okay. So, x double dot is nothing but d2x over dt square, and we are multiplying it by 2 x dot. So, which is dx by dt equal to minus omega square x into 2 dx divided by dt. Okay. Now, let us integrate this with respect to t. So, we have integral d2x over dt square into 2 dx by dt equal to integral minus omega square x into 2 dx over dt and dt. Okay. And this integral is nothing but dx over dt whole square. Okay. That will be equal to minus omega square x square plus some constant a. Okay, because the integral of dx over dt whole square will be 2 dx by dt and then the differentiation of dx by dt which is d2x over dt square. Okay. So, therefore, we have that. Now, let us find out a from the initial condition. So, let us say we have this spring mass system and when the spring is stretched by an amount a, in that case the velocity becomes 0. Okay. So, let us say at x equal to a dx by dt which is the velocity, that is equal to 0. So, we have 0 dx by dt is velocity equal to minus omega square a square plus a, and that gives you a equal to omega square a square. Let us put it back. So, we have dx over dt whole square equal to minus omega square x square plus omega square a square, and this is the velocity square. Okay. So, x dot square, this I can put it over here to find out the kinetic energy. So, T becomes half m into omega square I can take as a common factor a square minus x square. Okay. And what is m omega square? Remember, omega was square root k by m. So, let me just mention that omega was square root k by m. So, therefore, omega square m will be k. So, this I can write down as half k into a square minus x square. Okay. And let us put the kinetic energy and the potential energy in equation number 7. So, E will be T, T is half k a square minus x square plus V, V is half k x square. This will get cancelled with that and we have E equal to half k a square. Okay. So, therefore, the total energy of the harmonic oscillator is independent of x. Let us plot the kinetic energy, potential energy and total energy as a function of x. So, we have x and the maximum value of x is plus a or minus a. Half k x square is a parabola. Okay. And a square minus x square will be the inverted parabola and the total energy, which is the sum of both, that will be constant. Okay. So, this is the potential energy V. Okay. This is the kinetic energy T. And this is total energy E. Okay. So, you can see that since the friction etc. are not involved, therefore, the total energy remains conserved, and when the mass m moves, then the potential energy get converted into the kinetic energy and the kinetic energy gets converted into the potential energy. Now, let us look at the same system, okay, but let us say we rotate this configuration by 90 degree. Okay. So, let us look at the rotated system. By 90 degree. So, now the configuration that we have is following. We have a mass which is hanged by a spring, okay. And let us say when you hang the mass, then we have the equilibrium, okay. So, this implies that if the mass is not there, then the natural length of the spring will be smaller, and let us say this length is delta. Now, you stretch this spring so that we set up the motion, and let us say from the equilibrium we stretch it by an amount x. Okay. So, herein we have defined x as the displacement from the equilibrium position Now, let us look at the equation of motion of this system. So, the equation of motion will be summation fx equal to mx double dot. So, we have m x double dot equal to, let us look at the forces that are acting on the spring. So, that will be minus k times the total extension in the spring, which is delta plus x plus the weight of the mass which is going to act in the downward direction. Let us call this equation number 1. Now, in the equilibrium case, the forces will be balanced. So, mg will be equal to k times the extension which is delta. Okay. Let us put it above. So, we have m x double dot equal to minus k delta minus k x plus mg, but this mg will get cancelled with k delta. Therefore, we have m x double dot equal to minus kx, and this equation of motion is identical to the horizontal case that we have studied. Okay. There is no difference when you study the spring mass system in the horizontal configuration or in the vertical configuration. Okay. So, the equation of motion remains unchanged. Okay. With this, let me stop here. See you in the next class. Thank you.